Hello and welcome to this talk, Avoiding Bias when Estimating the Consistency and Stability of Value-Added School Effects. I'm George Leckie, Professor of Social Stats at the Centre for Model Modelling, School of Education, University of Bristol. So in the education effectiveness literature, there is a great interest in estimating the effects that schools have on student learning. And once you've done that, there is, of course, then secondary interest in whether those school effects vary across academic subjects, but also are the effects that we estimate schools to have on student learning, are they stable from one academic cohort of students to the next? Do they repeat year after year? So the way this is done in the education effectiveness literature is to fit multi-level value-added models. So these are glorified regression models. What they'll do is they'll regress students' current achievement on their previous achievement some years earlier, and they'll include a school-specific effect in those regression models. And effectively, the multi-level approach will allow us to assign values to those school effects on student learning, or sometimes it's called progress that students make between the previous score and the current score. That journey over time, are there school differences in the average improvement that students make? Having said that, within that kind of multi-level value-added model literature, when we look at applications of this, which report correlations in how consistent school effects are across English, maths, and science, or how stable they are from one cohort to the next, those correlations come actually from three different variants of that multi-level approach. And that has been done under the assumption, really, that they all give the same answer. They're just being kind of used interchangeably. What we show in this talk is actually that these three different popular approaches for estimating these correlations off the back of multi-level models actually give different answers. And we explain when they'll give different answers and why they give different answers and in what scenarios you need to worry. That is the focus of this talk. Now, all of this is written up in a journal article in the journal JEBS, so full details are available there. I'll be presenting the highlights in this talk. So a bit of motivation. In England, school league tables are published by the government, which report the estimated school effect of every school in the country on students' learning. Now, they do this both for overall achievement, but also separately by academic subject, English, maths, science, and so on. And so we have 3,000 secondary schools, and so we'll have 3,000 sets of results, 3,000 scores in English, 2,000 in math, 3,000 in science. And you could, of course, correlate those to give some overall summary measure of how consistent school effects are across the subjects. And here is the same kind of thing now for Bristol. There's 20 schools in Bristol, but for the country as a whole, there's 3,000 secondary schools. And here are the school effects in 2017, 2018, 2019. And so again, there's interest in how correlated those columns of school effects are for the country as a whole, because that's a summary measure of the stability of the system. So what I'll now do is describe the three different approaches that academics use interchangeably to actually put a number on those correlations of interest. So as I said, the traditional approach is to fit a multi-level regression model. So a little bit of notation here, YIJ would be the current achievement of student I in school J, let's say in English. Regressed upon their English test scores some 3, 4, 5 years earlier, whatever it is, and maybe some socio-demographic characteristics. Now, having kind of established that national relationship, some schools do better than others, and that's picked up by the UJ, which is the school random effect. And so they'll estimate this glorified regression model, and then post-estimation, we will predict these residuals, assign values to them. And we do that by something called empirical Bayes prediction, which is sometimes called shrinkage estimates. Crucially, we'll fit this model twice, and separately, once for students' English scores, and then separately for the same students' math scores, two separate models, two separate sets of school effects, two new columns in our data set, which are the school effects in English, school effects in maths, and then we could just correlate them with a Pearson correlation. And that is approach one. And here are some correlation matrices from a paper which used this approach, Gary Marks, on some, I guess, Australian data in reading, writing, spelling, and grammar. Here's a correlation matrix on fitting 4 separate models, getting the school effects and correlating them, just as an example. Now, the second approach, which I'm calling the modern approach, is to first sellotape those two separate models together for English and maths. So I've written two equations now, the top equation for English, the second equation for maths. You can see the two school effects of interest in there, U1J and U2J. And because I'm writing this as one big model, what this shows is that implicitly, when you fit two separate models, we're implicitly assuming no links between those two equations, no correlation between the two school effects. Well, the very thing of interest is the correlation between the two school effects. So rather than predicting school effects and correlating them after the event, let's correlate them directly in the model of interest by unconstraining this correlation, which is implicitly constrained to 0, and freely estimating it. Similarly, within schools, some kids do better than expected in English, and those kids will tend to also do better than expected in maths. And so we shouldn't be imposing a correlation of 0 there either. We should freely estimate that. So in the joint model, we estimate 2 extra parameters. And this is the model now that we've removed those constraints and are now estimating those 2 extra parameters, which is a correlation in the school effects, the very parameter of interest, but also a correlation in the student residuals. So if we fit a joint model to the same data and directly estimate the correlation, these are the kind of correlations we might get. So this is from a paper by Leonardo Grilli on Italian data. He had 3 equations for reading, maths, and science, and so estimated a 3x3 correlation matrix directly. So a different approach. Now, the third approach, which I've seen in the literature, is to correctly fit a joint model to English and maths, but rather than reporting in the journal article the correlation which is estimated directly, to nevertheless predict the school effects for English and maths from the joint model and to calculate the correlation of those predictions and report that. And that's a different correlation again. So here I've written the model out again once more, which is the joint model where we freely estimate the correlation of interest at the school level and also the student one, but rather than reporting that row U12 directly, we get predictions of these U1s and U2s as residuals, 2 new columns in the data, and do a Pearson correlation on that. And that's going to be a different Pearson correlation to the very first one from approach 1 and different from here. So 3 different approaches, 3 different numbers. And here is a paper which is by Sally Thomas, which followed that approach. So we now want to kind of establish that these different approaches give different answers on the same data. So let's compare the traditional approach to separate models, okay, to the joint model, which directly estimates the correlation. So one way to do this is to simulate data from the joint model, but fit back 2 separate models. So that's what I do here. I simulate data for 1,000 schools where the true consistency of school effects across English and maths is 0.5. I fit the model to that big simulated data set, sorry. I predict the 2 sets of school effects, 2 columns of numbers. I do a scatter plot of them. I report the Pearson correlation, and I only get back 0.3 when the true value was 0.5. So it's biased downwards. Now, in the literature, there's been some slight awareness that these different approaches might give different answers, and people have kind of rather casually kind of said, oh, we'll just do this or that, or it's this explanation or that explanation. One explanation is that these predicted school effects are so-called shrinkage effects, which pull all the school's scores towards the overall average, and to a greater extent if it's a small school. So if we just remove that shrinkage, which has been suggested in the literature, we still get the same correlation 0.3. Now, these are very noisy estimates because there are not many kids per school, and so the shrinkage is trying to control that, but in a way it over-controls And so there's something else that's been proposed called reflated, which gets the correct variability for English and maths. It might get the correct variability for English math, but it's still got the incorrect covariability, if you like. So fiddling around with these residuals isn't really helping us here. It's always 0.3 when it should be 0.5. Now, because this problem is relatively simple, we are able to kind of show an analytic expression for that naive Pearson correlation from the two columns of numbers, how that relates to the true parameters. The terms in black are good, the terms in orange are bad. So it's the presence of these additional terms in orange which is causing the downwards bias, leading us to get 0.3 instead of 0.5. So off the back of that expression, it's nice. We can then map out the magnitude of the bias depending on the features of the data. So this is just a visualization of that equation. So we have three panels here. ICC equals 0.05, which is a small school effect setting. You can imagine this is a Scandinavia utopia where schools don't vary so much in their effectiveness. In the middle, maybe of England, 15% of the variability in progress is between schools, and then 25% of the variability in progress is between schools. Perhaps this is more maybe developing countries, or maybe somewhere like Chile, where there's big school differences. Now, on the x-axis, we've got from 0 to 200 kids per school. So on the left, primary school settings, on the right, secondary school settings. Now, I've drawn this picture such that the true correlation is 0.5, which is the horizontal black line. But what we actually get back from fitting two separate models are depicted by the blue lines. And we've got multiple blue lines because what you get back depends, it turns out, on the residual student correlation. So remember, this is capturing if a student does better than expected on English, that is informative as to whether they'll do better than expected on maths. And the strength of that correlation at the student level matters. And so that orange dot relates to a scenario where there's only 10 kids per school. We've got very small school effects. So it's a primary school setting in rural Scandinavia, if you like. The true correlation is 0.5, but the student correlation is 0.2. And what we get back is 0.3. So essentially, the estimated school correlation from approach 1 is pulled towards the true student one. It's biased towards it. But crucially, the magnitude of all biases reduce as we move to more unequal school systems, and they also reduce as you move from primary to secondary settings, and they also reduce as the student correlation approaches the school correlation. Okay, take a breath. Now let's compare approach 3 to 2. So approaches 3 and 2, in both those, you do fit the joint model, which is the correct model of interest. But whereas in approach 2, you directly report the correlation, the school correlation, which is a model parameter now. Approach 3, we have this rather convoluted approach that despite having that correlation, we go ahead, predict two sets of school effects from the joint model, and we'll do a Pearson correlation of those. And the latter will differ from the directly estimated correlation. So again, on exactly the same simulated data that I had before, I fit that joint model, as I said, get two sets of school effects and correlate them and get a correlation of 0.66 when I really wanted the 0.5. Now here, reflating those shrunken effects, so not reflating, unshrinking them, will actually lead to correlation of 0.3. Okay, so now they do differ, but we wanted 0.5. Well, we can get 0.5 by reflating, but the process of reflating makes use of the directly estimated correlation of 0.5. So, of course, it gives the correct answer. But if you want the correct answer, you don't need to have this convoluted process. You've directly estimated that parameter of interest. So for this approach 3, we can also have an analytic expression for the nature of the bias, effectively, in approach 3 versus approach 2. And we can plot that in the same way as we did before. And the key difference here is it's like a mirror image around the line of 0.5. So whereas before we were getting downwards bias correlations, here we're getting upwards bias. So remember, we got 0.66 instead of 0.5, whereas previously it was 0.3 instead of 0.5. Then approach 3 is upwards biased because now the what you get back, the Pearson correlation you get back, is now not pulled towards the student correlation, but is actually repelled away from the student correlation, is the way that the maths work. But because approach 2 is correct, approach 1 is downwards biased, approach 3 is upwards biased, we've actually got 3, 2, 1 in terms of these three correlations, and it could be a sizable range. So to look at what this looks like in practice, let's take some real data now. Application to England. This is a primary school setting, which is where the differences will look larger. But other than that, we look at English and math scores at age 11, regressed on earlier achievement at age 7. We fit 2 separate models. We also fit a joint model. And when you fit a joint model, you get 2 extra parameters. Crucially, you get the parameter of interest, the consistency of school effects correlation, 0.786. So this is approach 2. When we fit 2 separate models, get out the predicted school effects and correlate those, instead of getting 0.79, which is the true correlation, we only get 0.69, so we're 0.1 lower down. And fiddling around with that doesn't really change anything, which is what theory suggested. And if we do an approach 3, which is where we do fit the joint model, but rather than reporting 0.79, we get out the 2 school effects and correlate those, it goes up to 0.84. So we've got a range of 0.15 in the correlation between approach 1 and approach 3. Sorry, this should say approach 1 here. So that's, I'd say, sizable using real data. So to conclude, the traditional approach to estimating consistency of school effects, but also the stability of school effects across 2 cohorts, is just to fit separate regression models to each subject or each year, and then correlate the residuals. But that will give a different correlation to if you fit a joint model. We argue that the joint model is preferable. You're directly estimating that system-level summary parameter of interest. But then again, there's this third approach where you do fit the correct model, but nevertheless, you get out the predictions and correlate those, and you get something different again. Now, the magnitude of these biases are going to be larger in school systems which have smaller school effects. So that's your Scandinavia, Utopia. They're going to be larger in primary school settings rather than secondary school settings, but they're also going to be larger when the student correlation diverges from the school correlation of interest. So there you go, 3 different approaches used in the literature, naively being treated as interchangeable when in fact they give different answers, but we've now revealed that. So thank you very much for listening, and I hope that was interesting. Thank you. Bye-bye.